Before we start, make sure you are familiarized with geometry, trigonometry, and the law of sines. The following is the proof and examples for the extended law of sines. The extended law of sines uses trigonometric principles to help find information about a triangle or circle the triangle is inscribed in. You start with any triangle. Label the corners A, B, and C, and the side opposite those corners a lowercase a, b, and c, just as you would for a law of sines problem. Next, you draw the perpendicular bisector of each side. The point at which all of these new lines intersect is the circumcenter. In this example, the circumcenter is within the triangle, but it isn't always, which I'll explain more later. The circumcenter is equidistant from every vertex of the triangle. You can work this out by noticing it is in the middle of angles A and B because it lies on the perpendicular bisector of side C, and it is in the middle of angles B and C because it lies on the perpendicular bisector of side A, and therefore it is in the middle of angles A and C because it lies on the perpendicular bisector of side B. Label the circumcenter point O. As point O is equidistant from every corner, you can draw a circle around your triangle with the circumcenter at the center, with every vertex of the triangle resting on the circle. This circle is the circumcircle, and the distance from the circumcenter to any corner of the triangle is the circumradius, or the radius of the circumcircle. Add a point D where the perpendicular bisector meets side C, then add the circumradii from angles A and B to the drawing. Now everything is set up for the actual proof. Notice the length of point D to point B is side C over 2, and that the triangle DOB is right-angled. Using the inscribed angle theorem from geometry, you can find that angle C equals 2 theta, where 2 theta is angle AOB. But since line DO bisects it, theta equals angle DOB, and consequently, theta equals C. Therefore, using the right-angled triangle DOB, you can find that the sine of angle C equals side C divided by 2 over R, which becomes side C over the sine of angle C equals 2R. You can find that by repeating this for angles B and C, we arrive at the full law. Side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C, which equals 2R, where R is the circumradius. Now the circumcenter isn't always within the triangle. When it is outside of the triangle, such as in this example here, it changes how you can prove the law. Angle A now describes the outside angle rather than the inside one. This changes the angle inside triangle DOB to 1/2 times 2 pi minus 2 times the angle A, which simplifies to pi minus angle A. And since the sine of pi minus angle A equals the sine of angle A, the law and the rest of the proof remain the same. Some vocabulary to remember. The circumcircle is the circle surrounding a triangle, Every triangle has a unique circumcircle. The circumcenter is the center of the circumcircle, and it is often found inside the triangle. The circumradius is the distance between the vertices of a triangle and the center of the circumcircle. It is also the distance from any point along the circumcircle to the circumcenter. Thank you for watching.